Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd Edition by Briggs, Cochran, and Gillette. I am writing this video and we're gonna mark it optional. If you're like me, I don't like being told a rule and said, hey, just do the rule, believe me. And what I'm going to do is I'm going to prove that the power rule is true. Now, something I need you to understand before I can do that is the binomial theorem. This involves combinatorics, this involves Pascal's triangle, this involves a whole lot of stuff. But here's what I want to say. I want to start with Pascal's triangle, which if you recall, I hope you were taught it. I'm starting to learn from my high schoolers that there are gaps where they did not. Every number is the sum of the two numbers above it. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3. And I can keep this pattern going forever and ever. Now, I can write row and column as, so if I wanted 3, choose 1, I would go. This starts weird because it starts numbering at 0, so 0, 1, 2, 3. I go 1, 2, wow, I cannot even number today. That's a 3. This one is 4. I go down to 3 over 0, 1. So 3 choose 1 is 3. Now, what this allows me to do is if I have x plus h to some number n, I can break this out, I can expand this out as x to the n plus n choose 1, x to the n minus 1, h plus n choose 2, x to the n minus 2, h squared. And I do that forever, and then at some point I come back and it's n choose n minus 1, x h to the n minus 1. And then h to the n. Now, I have to have this, and I'm going to explain why. So, to prove that, and I'm going to use the same definition I used before, for any integer n, then d dx x to the n is n x to the n minus 1. Okay, proof. And this is going to be on multiple pages, so I am going to have to switch around. Let the integer, fun set notation for integer. That, by the way, that is a Black Forest Bait Z. It is the worst Z I've ever drawn, so I'm going to redraw it. A blackboard bold font Z, and that's because the German word for number is Zahlen. Now, so n is an integer, and we're going to say it's any integer, so I'm going to say it's arbitrary. Okay? Now, I am about to work a limit definition for x to the n using that tried and true definition. So, just going to scoot this up a little bit because there's no way I'm going to have enough room here. So, I'll tell you what, let's just start the next page. So, by the definition of the derivative, the derivative with respect to x of x to the n is the limit as h goes to 0, x plus h to the n minus x to the n and all of that over h. I apologize for trying to make that plus. Now, this is where the binomial theorem comes in. This expands, limit as h goes to 0, as x to the n plus n choose 1 is n, x to the n minus 1 h plus n choose 2 x to the n minus 2 h squared plus, and it goes on forever, and somewhere along the way it stops at h to the n. Now, I then subtract x to the n, all of this over h. X to the n minus x to the n is 0. Here's where we've really got to stop and think and pay attention. Every term in this expansion has an h in it except for the first one, but we just canceled the first one. So this has an h, this has an h squared, the next one has an h cubed, the next one has an h to the fourth, and it goes on until I hit h to the n. Every one of them has an h. So since all of them have an h, I can factor out an h. So I've got h times n to the n times x to the n minus 1 plus n choose 2 x to the n minus 2 h plus dot 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 all the way down h to the n minus 1 all over h. Now here's where the magic happens. We're taking a limit, so I can ignore the fact where h is 0 and I can treat that as if those cancel. Now I'm left with a polynomial. Limit h goes to 0, n x to the n minus 1 plus n choose 2 x to the n minus 2 h plus h to the n minus 1. Now just like before, this is a polynomial, I can just plug in 0 for h, but what I want you to see is every term has an h except this one. So what I really have is I have n x to the n minus 1 plus this times 0, but that's 0, don't care, plus something horrific times 0, so squiggly line for something horrific times 0, plus something horrific times 0, plus da da da, all the way down to just 0. 0 to the n minus 1, but 0 to any power is 0. Everything else cancels except this term. So, since everything else is 0 and adding up a whole bunch of zeros is still just 0, the derivative of x to the n is n times x to the n minus 1. That takes care of it. Now, this rule doesn't really work that well with negatives, which is probably why the definition in your book is set up the way it is. But we're going to see moving forward that I can treat them the same way, and we're going to talk about that more as we get into the quotient rule. If you're like me and you like having things proven to you, then I hope you've enjoyed this video and you found it useful. This just proves I don't care what the power is, its derivative is that power is the coefficient and the new power is one less. Thank you and have a good day.